So the task is for each of these English letters and numerals thought of as a subset of the XY plane to classify them according to the fundamental group of that letter. So if I'm thinking about the letter F, for example, the question is, if I choose a base point inside of my F, maybe I'll put it right there, something like that, and if I draw a loop inside of my F, which is based at that base point, any which way that I would like to draw my loop, maybe it looks like this, who knows, right? Is that loop contractible?
Yes.
Yeah, sure. It certainly looks like it is. Is it possible for me to draw any non-contractible loop inside of this F? I feel like the answer is no, right? And so what would we say is the fundamental group of the letter F, thought of as a subset of the XY plane? If everything is contractible, that means everything is homotopic to everything else. And so the group of homotopy equivalence classes of loops inside of my F, if everything is homotopic to everything else, that means there's no difference between any two curves, which means they all belong to the same homotopy class. And so the number of elements in my fundamental group is 1. So every single loop inside of my F is homotopy equivalent to the constant loop, which never leaves home, the loop that just remains at the base point. So in shorthand, I'm just going to kind of write pi 1 of F, thought of as a subset of the XY plane. It only has a single homotopy class in it. It's just the homotopy class of the constant loop. Everything is contractible. So it's a group that has only a single element. So we might say that it's a trivial group. And so on your sheet, you're going to have one collection of letters and numbers whose fundamental group is trivial. So F is going to be one of them. Right? And so then you might go about asking, okay, what other letters and numbers have a trivial fundamental group? And once you find an example of a letter or a number which does not have a fundamental group which is trivial, then classify all of the other things on here whose fundamental groups are like its, like non-trivial in the same way. And then you might not need to use all 4 of these categories. Put that out there as another hint. We found out that there are really only 3 categories of like which fundamental group these letters and numbers have. That either the fundamental group is trivial in cases like F, C, G, N, 5, and so forth. Or we can classify by how many generators there are in the fundamental group. And how could you tell how many generators one of these letters or numbers had? What were you looking for?
Punctures.
Yeah, you're looking for the punctures, right? In the analogy to the punctured plane. So what's the classic example of a 1 generator fundamental group for one of these letters or numbers? What's a 0, right? A 0 or an O, right? Because this missing space here in the middle is your puncture, and so it gives me something to wind around, right? Something I can measure the winding number around. And as we said, having a puncture means that 1 trip around is different from 2 trips around, is different from 3 trips around, and so forth. And so every puncture that I put in gives me a free generator for my fundamental group. So when I have 1 puncture, as in the example of 0, but what other letters and numbers up here also have a single puncture? 9 does, 6 does, 4 when it's drawn this way, right, as opposed to the handwriting way, which is like an H, kind of, right? R does, A does, P does. So yeah, so a whole bunch of these have 1 generator that's attached to them. And when that's the case, usually what topologists will do is they'll say, well, given that every infinite cyclic group is isomorphic to the integers, we'll just write that the fundamental group is just isomorphic to the integers. Right? With the number 1, the role of the number 1 inside of that group of integers is the role that's being played by this 1 generator. Right? It has infinite order, because if I compose it with itself, I keep getting different things every time, infinitely far. And it has an inverse, which we decided was just the oppositely oriented loop around that puncture. And then we can define it in that way. When we have two generators, so what's an example of a two generator, of a letter or a number with a fundamental group having two generators? 8 is, I think, kind of a classic example. Because here we have two punctures, one at the top part of the 8, one at the bottom part of the 8, and they're independent from one another. So that if I were to place, for example, a base point right in the middle of the 8, right here, then I could take a loop around the upper puncture and get one generator for one factor in my group, or I could take a loop around the other lobe, the other puncture over here, and get a different generator. And we flailed a little bit, by we, I guess I mean me, in our last class, at justifying what happens whether or not those two generators commuted with one another. We tried to write down either talk ourselves into or possibly talk ourselves out of those generators commuting. And I think we didn't clean up this mess, but it does turn out that those two generators do commute. We were kind of flailing about this last time. But if I think of A as being my generator, which goes around one of these parts of the 8, and maybe B is the one that goes around the other way, then it does turn out that AB is equal to BA, or is homotopy equivalent, right? The concatenation of AB is the same as the concatenation of BA. And so what we end up with, because these two things commute with one another, is we get a group that sometimes in group theory is called the Cartesian product, Z cross Z. In other words, to specify a homotopy class of base loops inside of the fundamental group of this 8, for example, all I need to do is specify two winding numbers, an ordered pair. Tell me how many times we wind around the puncture on the top, tell me how many times we wind around the puncture on the bottom, and that completely classifies the homotopy classes of base loops inside of my 8, right? So it's like n comma m, where the n's and the m's are integers. And all of my addition that happens inside of this group happens component-wise. So if I tack in one more loop around this top lobe, if I increase this n by 1, all I have to do is just increase that number in the first entry of my ordered pair by 1. So it really is, this relationship going from Z to Z cross Z is just like the relationship between when we go from the real number line to the XY plane, right? The x-axis sits inside of the xy plane, or the y-axis sits inside of the xy plane, or really any line sits inside of the xy plane in a whole host of different ways. But really, when we go from one generator to two, it's like going from one basis vector to two basis vectors, one dimension to two dimensions. And in each of our dimensions, all we're specifying here is how many times we wind around the respective puncture. Right? So we could say up to isomorphism that this fundamental group is just Z cross Z. And if you want to be fancy, sometimes you'll call this Z2, in the same way that we say R2 when we're talking about the XY plane. But it's only because we have the commutativity of those generators that we get away with writing it as Z2. Otherwise, the operation inside of this group wouldn't be so nice as to just operate component-wise on the factors of this product. We would have something nastier. And if we were studying deeper into group theory, we would call that nastier process a semi-direct product, as opposed to the Cartesian product, which is sometimes called a direct product of groups. But if we don't have commutativity, then we have to be a little bit more careful about how we write these things. So for the English alphabet, those are seemingly the only three possibilities: trivial, isomorphic to the integers, isomorphic to Z2. Z squared, maybe we should say. And so if we want letters or numbers that have a fundamental group that's more complicated, we have to reach into some different alphabets. But another place that we could have reached, and this goes to the last question on the sheet, I specifically chose uppercase letters for this exercise, because if I had allowed lowercase letters into the mix, then we could get some other interesting stuff happening. For example, lowercase j. So if I think about a lowercase j as my topological space now, what would be the fundamental group of this thing? This is similar to the question at the bottom of your sheet, which asks you to think about the two-digit number 10. So a 1 and a 0. If we consider our topological space as being one of these things, how does that change our conversation about what these fundamental groups actually look like or what they're able to encode for information?
Well, you have to leave one, like if you put your base point, let's just say in the 1, you'd have to leave that and go into the other, into the 0.
Yeah.
And I don't know if that's...
Right, so for the first thing we have to do in determining the fundamental group of a topological space is we have to put the base point somewhere. Right? All of our loops have to be based from a common point, starting point, so that we're able to concatenate them together, right? So that the ending point of one loop can be the beginning point of the next loop that we're gluing together when we do the operation in our fundamental group. So as soon as we choose a base point, we are locked in to either basing all of our loops inside of my 1, in which case they would all be contractible, because the fundamental group of the number 1 as a subset of the xy plane is trivial. Or if I place my base point in the 0, I get a different answer. And that doesn't seem very satisfying, right? Same thing with my j, in a way, right? If I put my base point up here, I get all of my loops have to reside up here in this circle, up here at the dot of the j. If I place my base point down here, all of my loops have to reside down here in this other part of the j. So this choice of base point matters now. Did the choice of base point matter in all these uppercase letters and numbers?
No.
Doesn't seem like it. So what's the distinguishing characteristic? What's different about these than these? Actually used a different word a minute ago. It's a slightly different word. I'm going to... Yeah, I actually want to tag on it because this is the precise term used by topologists in talking about these things, disconnected.
That's an easier word.
It's an even easier word, yeah, exactly. But it is the word that we would use to describe these two situations. And in fact, to put even a finer point on it, they're disconnected in a particular way. They're called path disconnected. It means that there exists a pair of points inside of these spaces which do not have a continuous path that connects them. Right? My green base point here and my pink base point over here, they're in totally separate universes from one another. We can't draw a continuous curve that connects one of these to the other. If we could, then it wouldn't matter if I chose the green one or the purple one, because any loop which was based at the pink one, I could consider instead to be a loop based at the green one. I just have to start at green, travel over to pink, do my loop, and then come back to green. As long as I have a path that joins these two together, then it doesn't matter which one of these two I choose. But there is no path, continuous path, joining the green to the pink. And there is no continuous path joining a point up here to a point down here inside of my J. All of these figures are path connected. Or maybe another way to say it is that these all have one path component. Whereas the lowercase j and the number 10, they have two path components. And so even if we compute the fundamental group of a path disconnected space, then our answer is going to be different depending on which path component my base point resides in. Actually, for the lowercase j, the answer is the same, really, because both of my path components are contractible. But for the number 10, it matters, because one of my components is contractible and the other is not. So the way that topologists resolve this difficulty is that they have another group called not pi1, but pi0. Pi0 of, let's say, my lowercase j. This is going to be the zero-dimensional homotopy classes. So instead of being loops that we're just drawing constant loops that always reside at a single point, like a zero-dimensional loop, if you like. And these are going to come in two flavors. We're going to have those loops that are based in that dot, and then those loops that are based inside of the j portion. So the zero-dimensional homotopy group, sometimes called the path group, if you like, for the lowercase j, has two components in it. Two elements in this group, one for each possible path component. Whereas the pi 0 for all of these just has a single element in it for the one path component that's there. So, so the purpose of that last thought exercise at the bottom of the page was to introduce that idea of path connectedness or path disconnectedness, and that there's another topological object, pi 0, that distinguishes one of those from the other. So for path-connected spaces, this has only one element. For non-path-connected spaces, it has more than one.